Welcome engineers, Hassan here. Today we are talking about floating point numbers. The way they are represented in most cases is described in the IEEE-754 standard. We have already covered how 5 in decimal is 101 in binary. In case you forgot how we do this conversion, I encourage you to watch the video on binary integers first. The link is in the description. The question we haven't talked about yet is how we represent real numbers in binary, like 0.5. Well, we can express it as 1 over 2, or 2 to the power of -1. And once we have figured out the exponents, we can write down the number in binary. In this case, we write 1 located at one position to the right of the decimal point. So 0.5 in decimal is 0.1 in binary. Easy, right? Let's look at another example. How do we write down 5.75 in binary? As usual, we express it as a sum of powers of 2, write it in exponent form, and it tells us where to put ones. And now we can save it as any other binary data. But there is one problem remaining. It's this dot in the middle. How exactly are we going to represent it in binary? Remember we talked about standard scientific notation last time? It will come in handy here. First, let's normalize our number. We need to have exactly one whole digit in front of the decimal point. By moving numbers 2 places to the right, we have basically divided by 2 twice. We need to offset this difference by multiplying the number by 2 to the power of 2. This is the expression we need to encode. Before we do that, we can make several observations. First, the number 1 in front of the decimal point is constant. It is going to remain the same for all values except exactly 0. Hence we can drop it. Base 2 is also going to be constant since we are dealing with binary. We can drop it as well. Finally, we need to distinguish positive and negative numbers. In order to encode a sign, we would need an extra bit. So, once we remove everything we don't need, we are left with a sign, a fraction, and an exponent. These are 3 values we need to encode. We do this by designating parts of our bitset to each value. In a 16-bit number, we will have 1 bit for a sign, 5 bits for an exponent, and the rest 10 bits for a fraction, often called significand or mantissa. I prefer the term fraction in this particular case because that's what we store, a fractional part of a significand. The term mantissa is used for both depending on the context. Now let's encode this. To encode signs, we use the previously explored idea of sign and magnitude representation. We will simply encode positive numbers with 0 and negative ones with 1 at a sign bit. So here we will change a plus sign into a 0. Now let's encode an exponent. Here we have an exponent with a value of 2 and 5 bits to represent it. Should be easy to encode, right? The first thing to know is that there are 2 special values for exponent. All ones and all zeros. All ones can represent infinity or not number values, while all zeros reserved for a value of 0 or for values that are too small to represent, called denormals. When we encode 16-bit numbers, we have 5 bits. In 32-bit numbers, it's 8 bits, and for 64-bit double precision numbers, it is 11 bits for an exponent. This should give us a wide enough range. 5 bits give us 32 different values, but 2 of them are reserved for special values. This leaves us with 30 values we can encode. The smallest one has one rightmost bit raised, while the largest has all bits raised except for the rightmost digit. The one on the left has a value of -14, and the right one is 15. You may notice that the left one looks like an unsigned integer 1, and the one on the right looks like 30. We already know 3 different encodings for signed numbers, but this doesn't look like any of them. The way we decode an exponent is by subtracting half of the range from it. In this case, we subtract 15. This value is called bias. 1 minus 15 gives us -14, and 30 minus 15 gives us 15. When we use more bits to encode our number, the bias will also increase. Now let's get back to our example and encode the exponent. We add bias to our exponent value, which gives us 17. Now let's encode it in binary and we are done. All that is left is to encode the fraction value. This is the simplest part because we just copy digits to our bit set and fill the rest with zeros. And just like that, we have encoded a decimal real value in binary. Let's talk about a limitation of such encoding. When encoding a fraction, it may be larger than in this example. If our number had more fraction digits than 10, we would not have enough space to fit all of them. This is why we may lose precision. In that case, we may use a larger data type or accept a loss of precision. Some fractions have repeating values, like in the example of 1/3. Such values will never fit, no matter how many digits we use. That's why we say that floating point numbers have limited precision. There are 3 special values described in this standard. To encode a 0, we set all bits to 0. We may set the sign bit to 1 to get a -0. If all the exponent bits are set to 1s, but all the fraction bits are set to 0s, this would represent infinity. Infinity can also be a positive or a negative one. And if all the exponent bits are set to 1 and at least one fraction bit is also set to 1, it represents another number value called nan. Usually it represents an arithmetic exception, for example when dividing 0 by 0. To wrap up, let's introduce the formal definition that you can see on the screen. Feel free to download this image as a cheat sheet if you spend a lot of time with floating point numbers. This has been a quick overview of floating point number representation. Leave your questions and comments down below. Thank you for watching.